Dr. Tony Edridge. Today I'm going to give you a brief overview and description of isolators and circulators. I work for M2 Global Technology, and I'd like to start by showing you what circulators are and what they do. They have three connections. We call them ports. I'll explain more about that later. And for example, if we have a signal coming in on port 1 on the left, then it will go out on port 2. It's like a roundabout. It goes round, keeps to the left, and comes out at the next port. On the other hand, if you had a signal coming in from port 2, it will come out on port 3 down at the bottom. And of course, if one went in on port 3, it will come out on port 1. You can also have circulators that go the other way around, counterclockwise, and they will keep to the right. The signal will keep to the right. Now, isolators are really circulators with an added component, and the added component is a termination down on port 3. The termination absorbs all the signal. It terminates it. There can be no reflections of the signal. It's all absorbed. So, for example, here we have an input signal on the left coming out on the right-hand side on port 2. Any signal that gets reflected somehow from an antenna that's broken, perhaps, would come back into port 2. And we do not want it going into port 1 where it might do some damage. However, since it's really a circulator with a termination on, that signal goes round to the left into port 3 where it's absorbed. And so this is an isolator which isolates the component, the antenna perhaps, on port 2 from port 1. And here are some examples of various types of isolators and circulators. These are drop-in isolators, and you can see that they have tabs on the edges. These are the connections that are then soldered onto the circuit in which they're dropped in and bolted down through these holes here. These are the terminations that absorb the energy that we described earlier, each one having tabs on the sides and terminations. Here you see coaxial isolators. They have coaxial connectors on the sides and also terminations to absorb the energy. And here are waveguide circulators and one isolator. Here you see the termination on the bottom of this isolator, and the energy will come in or out here and in or out the other side. This shows the components of a coaxial isolator. There is a circuit down the very bottom, and it joins the three connectors, the coax connectors, and it's surrounded both sides by the ferrite, or the black material, which is surrounded by dielectric, which just helps us match the unit and stop reflections. Then there is a ground plane. The ground plane completes the transmission line for the energy to flow around the circuit. Inside the ground plane is a little well in which we put the magnet, a pole piece to help the field be directed, and temperature compensating material, and finally a wrap which holds everything together and completes the magnetic circuit. This shows a close-up of the magnet on the left and the ferrite and dielectric on the right. The magnet has a little chip in it. You may just see it if you've got good eyes. And that won't stop it working. However, we have to be careful with little chips and dirt in the construction of these things, and we'll talk about those things as we go along. Here we have a description of the three major components inside the isolators and circulators. The first, the circuit, is one you saw. It's really a transmission line, or the center part of the transmission line, and it connects the three ports together, but it also allows a resonance to occur so that the ferrite can perform the rotation in the fields that we'll talk about later. Then there is the ferrite material. This is really the magic of the isolators and circulators. It causes the RF fields to rotate inside the unit and direct the energy the incoming signal through to the correct port. But it requires a magnetic field, a DC magnetic field, and that is why we have the third component, the magnets, which provide that field and create the ferromagnetic properties in the ferrite. Here we have a look at the interior construction of a coax unit, and the drop-ins are very similar to this. And we have a center conductor for the transmission line for the energy to flow in. And the other two yellow lines here represent the places where the energy flows on the green ground planes. And the ground planes, the surface of these ground planes forms the outside edges of the transmission line. Inside the transmission line, we have these electric fields. And the electric fields, of course, go through the ferrite material, which are these gray discs here. The magnetic field is caused by the two magnets, and the magnetic field is completed around these, through these arrows, by the wrap. The wrap helps that magnetic field. Now, these things are tightly compressed with screws so that there are no air gaps between the different components. If there were air gaps or any dirt or debris, or chips off the magnets, they would stop these units working and possibly break the materials inside. I want to talk a little bit about transmission lines. Here you have a wave on the left, and you see it's hitting a short on the right, and it just bounces back. Now, in regular electricity you have in your house, if you have a short, it's a disaster, but that's not quite what happens with microwaves. They act like real waves like you have in your bathtub. They slosh around. And so a short will just cause the wave to bounce back. And we have different ways of transmitting waves through circuits in microwave parts. A microwave is like a radio wave. Radio waves transmit through the air a long way, and they don't need a return path. All the energy goes from A to B without a return path. So we can capture the RF field, the radio wave, in a tube, and it will then propagate down the tube, down the waveguide, without a return path. And we can do the same thing with a coax tube. And again, the energy goes from one end to the other without a return path. The fields are different, of course. The field in the rectangular tube goes up and down here, but here it goes between the inner conductor and the outer conductor. We can cut this coax open and have two plates, and we call that strip line, and now the fields go again from the inner to the outer conductors. We can take one of these away, and we end up with microstrip. And again, the fields go from the inner conductor to the outer plate. These are all different ways in which we can have transmission lines for the energy to flow and the signals to flow through. We make our devices very reliably. There are preferred ways of making isolators and circulators. We do not use crimp lids. They might fall off. Beryllium is dangerous. Neodymium is not reliable. And we prefer these other methods to make our devices. I want to show you now a little bit about how these isolators and circulators actually work. The field is seen to change in time, and the dark area is where the electrons are coming together and then separating, and you can see them coming together and separating. And that's what would happen on this thing here. And if you put a signal on the left-hand side on port 1, it would come out evenly on port 2 and port 3, and you can see the thing is symmetrical. The magnetic field is going up and down. The electrons are bunched here and here, and so some of them come out this side and some come out on port 3. Now, when we apply the magnetic field, it's going to twist all these fields around like this. And here you see now the magnetic field is pointing down here, and the electrons are bunched around port 2. And so the energy will come out port 2, but not port 3. And so what happened with the magnetic field being applied to the ferrite is the ferrite twisted the RF fields around to create this different field pattern. And essentially that's how isolators and circulators do their magic stuff. How are they used? Well, they're used for a number of different purposes. One is to protect the power amplifiers, which would be this unit here, and here is our circulator with termination, which absorbs energy. They protect the power amplifiers from large reflected signals from antennas, which could damage the power amplifier. And so the energy gets absorbed here and not damaging the power amplifier. One of the problems with communications is that they have lots of signals going through one amplifier, which causes them to mix and create distortion products, and our isolators and circulators can reduce that distortion. We can also measure the reflected energy by having a tab on here, and it will tell the operators of the base stations that something's gone wrong if they've got a lot of reflected energy. And they can also be used to decouple several stages of amplifiers so that they don't interfere with each other. Don't forget that these microwave frequencies, signals bounce from one place to another if they have any reflections that they can bounce from. And they're difficult to stop. So here we see 2 amplifier stages and an isolator in between them to stop signals coming back and messing up this amplifier here. And here would be a tab that you can measure what the signal is that's coming back. Circulators can be used a little differently. One of the methods that's used chiefly is to have a single antenna for transmitting and receiving. But then you have to separate the transmitter and the receiver electrically, and that's what we're doing here. And so here's the antenna, and an incoming signal will then go into the circulator, go around, keep to the left, come out, and go to the amplifier for the input signal. The transmitter on the left here, however, goes into the circulator, keeps to the left, goes out, and goes to the antenna. And so the transmitter never gets to blow up the input amplifier. That's the object of this circulator. And if you combine several circulators together, you can combine lots of amplifiers together and add the power of the amplifiers then to feed one antenna. I'd like to talk about the specifications. When you test these units, you have to test them to the required specifications, and there are 2 kinds. There's the loss of power you get in the unit, that no unit is completely loss-free. There are 2 kinds of power loss. One is inside the unit, and we call that insertion loss. The other is external, where the power is reflected from the connector and the input circuit of the circulator or isolator. We call that return loss, or sometimes we measure it in terms of what is called VSWR, voltage standing wave ratio, or simply VIS. The other measurement we do is isolation. Isolation simply measures the difference between the power coming back into the unit and what you would see on the input of our circulator. How much does it isolate? Well, we measure all these in terms of power. We don't measure voltages very much. And the units we use are dB, decibels, that's short for decibels. And I'll show you a chart which gives you an idea of what dBs are all about. Remember I said we want to know what the difference is between the input and the output? That would be a ratio. The ratio might be 1, which is what we'd like to have for a circulator, that the output is the same as the input. So we have here a ratio of 1 down at the bottom, and that is 0 dBs. In other words, no difference. Think of it that way. You have a ratio of 1 between the two signals, input and output, no difference, 0 dBs. Well, if we have a signal that is 10 times bigger on the input, then it is 10 dBs. If it is 100 times bigger, it's 20 dBs. So you can see how the ratio, the number for the ratio, is compressed. 100 goes to 20, and it gets compressed even more. 1,000 would be 30 over here. 10,000 would be 40. So you begin to see the pattern. And if you have numbers less than 1, like 0.1, 100th, 1,000th, then this would be like a mirror image, and it all goes down below, and you have negative numbers. They'd be the same as these, but negative. So a fraction turns into a negative logarithm, a negative dB. So 10 dB would be a factor of 10 less, 1/10. Minus 10 dB would be a factor of 10 less. So we're talking about the reflected signals from each port. If you put a signal in, how much of it actually comes back to you? If it does come back, it's a loss of energy. Minus 30 dB, that represents a very small number, is 1,000th of the input signal. And that would be a very good return loss, to have only 1,000ths coming back. 15 dB is quite a lot more than that. It's something like 25 times less. And this formula here is the reflected power over the incoming or forward power, and then you multiply it by 10, and it gives you the number of dBs. And that's how these numbers are determined. Then there is the voltage standing wave ratio, which is essentially the same thing, but it's measured with a different parameter, the voltage, which I said we don't normally use, but sometimes we do. And we can convert from one to the other. VSWR is this factor here, which is the return loss. Just to show you that these numbers are real, and we can use them. So 1 is a perfect situation where there is no standing wave, which indicates there's no reflections. And 1.1 will be good. 1.5 will be very poor. And they reflect these numbers here, minus 26 dB and minus 14 dB. Another parameter we measure, as I said, is insertion loss. We lose about 0.2 dB sometimes. That's about 5% of the signal inside the unit due to things like electrical losses in the circuit and losses in the ferrite. If you get as much as minus 1 dB, which is about 20% loss, that is not very good. And the formula here is simply the output power over the input power, and you take the logarithm. The other and last important measurement is the isolation. Obviously, it doesn't apply to circulators because we don't have the termination in to make an isolator. And so we measure how much of the signal reaches the input. We put the signal in to measure this on the output. It'll be port 2 in the diagrams we've shown you, and we're looking at the signal coming out from port 1. And it's not meant to have very much at all for an isolator. And so if we get minus 30 dB, which I have here, which is 0.1%, that would be very good. Just a tiny amount, a tiny fraction of the signal coming back through the wrong way. And obviously minus 15 dB would not be so good. And here's the simple formula for calculating the isolation. Now all these things are actually measured by equipment, electronic equipment, and you don't have to figure anything out. The number comes up on the equipment. There are many, many different kinds of isolators and circulators, and that's because there are many frequency bands, and different power levels, different construction techniques. And so if you have any questions about some of these devices, please contact our engineers at the Application Department of M2 Global Technology. Thank you very much.